Good afternoon. Today I am going to take the class in abstract algebra. It's coming the third BSc Maths, one of the major paper. Today my topic is groups and subgroup. I am going to cover this video what is group and the properties and ideas of the group and also the subgroup. Yes, first introduction of the group. Definition. What is group? A non-empty set of elements G. So G is a notation of G. Is said to form a group if in G there is defined a binary operation. Okay, here the operation is star, such that A comma B belongs to and A star B is also belongs to. This is closed property number one. And number two, the element taken from the G, that is A, B, C, and this is a property of associative law. A star bracket B star C equal to A star B bracket star C. Number three, identity element. There exists an element E. This is an identity notation. This is a notation of identity in group. There exists an A star E equal to E star. You can write A star E or E star E. This gives, when you multiply with any element with 1, you get the same answer. That's the concept. This treated as a 1. So every A belongs to. Number 4, inverse. For every A belongs to A inverse. A inverse also belongs to such that A star A inverse equal to. Otherwise, you can write it A inverse star A equal to I. You get it I. If you satisfy 4 conditions, then it is called a group. So number 1, closed. Number 2, associative. Number 3, identity element. Number 4, inverse. Next. Yes. What is abelian group? So now important note. What is abelian group? A group G is said to be a abelian group if we satisfy A star B equal to B star. For every A comma B belongs, so we take an element from A, G, and you write A star B equal to B star A. If we satisfy this condition, it is called a abelian group. Next, let us see the problems in group theory. First one is show that the set of all integer with the binary operation, here operation is addition. Note the point. Is an infinite abelian. So here operation is plus. Another point you have noted, this is an infinite group. You have to prove the infinite abelian. What is the condition of infinite abelian group? Now only saw the definition of a abelian group. First you can satisfy 4 conditions and one more condition A star equal to B star. We will prove one by one. To prove infinite group, I take this Z. Z is a integer. Set of all integers. In operation is plus. To prove Z comma plus, you got the given. So mathematically Z is integer. You can write notation in Z. To prove Z comma plus is an infinite abelian group. First we prove one by one. First we have to prove what? Closure. We know that we can take any 2 elements from Z. We know that sum of integer is again integer. So I take 2 elements. One is A equal to 40, another is A B equal to minus 30. When you add both, you get it 10. 10 is also belongs to Z. Therefore here closure property is true. So first condition is satisfied. Next, associative law. This is a formula. As we saw the definition. In associative law, if you by operation star there, here is plus because they given the question with the respective plus. Addition is always associative. No need to check. Addition is always associative in Z particular. Anyway, I take from example, I consider A equal to 5, B equal to minus 10, C equal to 2. Take LHS A plus bracket B plus C. Just substitute the corresponding value. You get answer 14. 14 is also belongs to Z. That is very important. So left hand side. And take the right hand side. A plus B bracket plus C. You substitute the corresponding value. A equal to 5, B equal to minus C, get 40. So LHS equal to RHS. Therefore, A plus bracket B plus C equal to A plus B bracket plus C. Here associative law is true. Number 3 is the third condition. Identity. Here you can remember and just recall. Here 2 operations we are using. One is plus, another one is dot. This is for multiplication. You please remember my plus is always identity element 1. Identity element is plus and 0. In multiplication, you just remember. Okay, plus identity element is always 0 because we can add it. What is the meaning of identity element? You take any element from G, you can add with that element, it gives the same answer. So you can take any element from Z plus 0 will gives the, but so in plus 0. In multiplication is 1 by here, we are not using the multiplication here, just get the idea of the identity. So in the identity element of 0 belongs to Z, generally taken A, so 0 plus A equals A plus 0 to A for every A belongs to Z. Whatever element you taken from the set of integer, you can with 0, you get the same answer. So identity as M is also true. Next one is okay. Inverse. For every A belongs to Z, and the element minus A. Okay. In addition, plus inverse A, suppose G minus A. This is a inverse. In addition, okay, so minus A belongs to Z, such that minus A plus C equal to, or you can write 0 A plus minus equal to 0. When you add both element and you consider inverse element, your answer should be 0. Therefore, inverse x inverse, you can take any element from Z and opposite 5, suppose for example 5 minus plus 5 get cancelled, that is 0. These is the identity element inverse. And final one is commutative law. It's very simple. A plus B equal to B plus C. I consider A equal to 5, B equal to minus 3. I just substitute LHS equal to RHS. Therefore, addition is a commutative. Therefore, still come up place is an abelian group. So here I prove the abelian group. Next one. This is called cubic root of unity. Anyway, this is called cubic root of unity. This is standard result. You should remember the value. Standard 1 omega square. We used to study in complex number just together. Prove that S equal to 1 omega square is a finite abelian. This is a finite group. And then you have to note which one is group and operation. That's very important. A group is 1 omega square. We have to note this is a finite group. You have to prove this is a finite abelian group with respect to multiplication. Just from the table. Multiplication, no? So 1 omega, just multiply 1 into 1. You can multiply everything into 1, you get the same answer. So 1 into omega, 1 into omega. Now omega into 1, omega square. Omega into omega square, you get omega cube. See, you know the value. Omega cube value is always 1. And take last one, omega square into 1, omega square into omega cube. Again I take it 1. And omega square, omega power 4. Omega power 4. So omega power 4 you can write it omega cube into omega. We know the value of omega cube is 1, therefore omega. So omega power 4 equal to omega. I frame the table. Now I have to check this is a finite table 1 by 1. First you take closure property. Closure, what is the condition of closure property? You can take any two elements, multiply, the answer should be also in the same element, same group. Here all the entries in the table, you see the entries, all the elements in the group only. 1 omega. You have a group having 3 elements. 1 omega, so everything in the same. So therefore, all the entries in the table are members of G. Look at the table. Show that closure property is true. So first condition is true. Next one is associative. Multiplication, addition is always associative. Here 1 into 3 elements. No, I just substitute the formula. 1 into omega bracket in omega square equal to 1 into omega square. You see LHS equal to RHS. Here associative law is also true. Just identity. Identity element is what? Just 1 into 1 only. 1 into omega. 1 into omega square. Therefore, if you multiply with 1, you will get the same answer. No? So 1 is the identity element in this group. And final one is inverse. How to find the inverse element? The inverse of 1 is 1. I just go back to the previous slide. Then you can understand. Yeah. Wherever 1, just look at 1 node inverse 1. And here, omega node inverse omega. Just see the corresponding value. Omega node inverse omega. And next 1 here. So inverse of omega square is, just think of. You see, inverse of 1 is 1. I show the table. Inverse of omega is omega square. Inverse of omega square is omega. You see the corresponding one. Just see the upper level and write the corresponding value. And it satisfies the inverse axiom. And next commutative, last one, omega and omega square into omega is omega is always equal. So commutative property is 2. X comma dot is a finite equilibrium. Right? Means it satisfies all the conditions. Next problem. So very important. Importance. The identity element in a group G comma dot is E. Okay. What is identity element with respect to dot here? E. What we have to prove here? G is a group with respect to dot is a unit. What is the meaning of unit? In group we have only one unique element. That is the meaning. In group we have only one unique element, that is identity. We have only one identity element, no other identity element. So I have to let us prove how. Let E1, E2 be two identity elements. I consider two identity elements. One is E1, another one is E2. We have considered E1 as the identity element. Yes. Okay. What we plan? I consider two identity elements. End of the step, what will happen now? E1 equal to E2. Both are same only. Then I conclude whatever identity element taken from the G is always equal to other. So we have only one identity element. This is the idea of the problem. So E1 is identity element. So E1 into E2 equal to, you can write E2 into E1 equal to E2. And E2 E1 equal to E1 E2 equal to, just rearrange the term E2. Now consider E2 as identity element. So this is identity element. E1 and E2 equal to E2. E1 E2 equal to E1. When you multiply E2 you get E1. Need mark it number equation number 2. Okay, what will equal to number 2? When you compare both, what happens? When you compare both, LHS is RHS. So E1, E2 equal to E2. Instead of that, you can substitute E1 equal to E2. This is my result using 1 and 2. So what's the meaning? You take two different types of identity element. One is E1, another is E2. I got answer. Both are equal. So what's the meaning? There is no different types of identity element G. We have only one identity element, that is unique. Next one is okay. Another important result. Inverse. The inverse of an element in a group. See what we just now we saw the identity element. Next is inverse. In group we have inverse element, that only one inverse element, that is also unique. Let G comma dot be a group and E be the identity element of a group. Here I take two identity inverse A1, A2 into inverse of A. Here also I consider two different types of inverse. By the definition of inverse, I write it A1 dot A1 equal to A1 dot A equal to E. Suppose A2 inverse A dot A2 equal to A dot A to E. Again I can just equating 1 and 2. I got it what? A1 equal to A2. Inverse of A is unique. Okay, inverse of A is also unique. It's also important. Next I just tell the two definitions before complete the group. Finite group and infinite group. A group G which contains only finite number of elements is called a finite group. Okay. Finite is very simple. You can count them. And G which is not finite is called a infinite group. And next one more is order of an element. Order of how to find the order of a group. The number of elements in a group G is called the order of G and is denoted by O. This is a symbol of order of G. In case in finite group order is also finite, and in case infinite order is also infinite. So just to solve one example, G equal to 1 omega square. Here order of G equal to 3 because 3 members are there. This is the way to find the order of a group. Similarly, we can find the order of an element. Order of an element. Okay. The element raise the power that is equal to identity element. That is the if G is a group, you take G from A and then order of G is least positive integer M. There exists A power M equal to E and is denoted by order of. How to find the order of an element? In previous slide we saw the order of group. Here how to find the order of element. Take the element, multiply the m number of times, you get the identity. This is called the order. What is the subgroup? Here subgroup is H. Whatever condition satisfies G is also satisfied by H. Thank you so much.